What is up, everyone? Welcome back to the Marvel Project. My name is Kiro, and today we're going to talk about work, energy. So what is energy? Energy, it's like how much, a body can move. Okay? So we'll explain it. If an object has high energy, it can move more or faster, or it has the potential to move more than a body with low energy. Alright, and so there are two main types of energy. Okay, we have potential and kinetic. Alright, so what are these two? Potential energy is, it sounds like potential. Okay, it's how much it can move or how much it would be able to move, whereas kinetic is how much an object is moving. Alright, so if an object has potential energy, that means while it may not be moving, but it has the ability to move a lot. Okay, so we'll say if you had an object here above the ground, okay, if this is your ground, or an object here. This object is higher up, so it has higher potential energy, okay, more potential energy. It has a higher tendency to move than this object, okay? So that's potential energy. What about kinetic energy? Well, kinetic energy is how much an object is moving, okay? So velocity. Velocity and mass relate to it. So potential energy is the energy an object has due to its motion. Alright, so what are these, formulas? Well, potential energy, gravitational potential is the mass of the object times acceleration due to gravity times the height off the ground. It is. Kinetic energy, okay, energy in motion, linear kinetic energy, or translational kinetic energy, is equal to 1/2 mass times the velocity squared. Okay, and so this is the mass of the object times 9.81 of the acceleration due to gravity times the height off a neutral point. I'll get to that. Okay, and this is the mass of the object times the velocity of the object squared. Alright, so we'll get to it. Let's say you have an object. Okay, you've got a ball. Alright, and this ball is off the ground by h, a height h, we'll just say. Alright, so how much energy does it have? Well, it's not moving, and we know by our potential energy that the height is the mass of the ball, or the energy is the mass of the ball times acceleration due to gravity times this height, h. So this is the total energy. Okay, and what does that mean exactly? Well, this is how much it can move, alright? And so if we would compare it to a different ball that was down here, that was lower, alright? And we said it had a height from the ground, h1. Well, its energy is its mass times gravity times h1, okay? And we assume, identical balls, the masses are the same. Well, h1 is smaller than h, so this ball's energy is less than this ball's energy, which means it will move less than this ball will move when you drop them. And that makes sense because this is lower, okay, it's closer to the ground, gravity will act less. So it has less potential to move. Okay? Now what if a ball is already moving? Alright? So let's say here you've got a ball and it's moving with a velocity. Okay, and then we know by our kinetic energy formula, alright, and the ball is mass, that its kinetic energy is 1/2 mv squared. Okay, so what does this 1/2 mv squared mean? Well, the ball is moving, and this is a measure of how much it's moving, you know, how much it's going with. So if you have a smaller mass, it has less kinetic energy. It has less energy in motion. All right, and a larger mass has greater energy. So how do you change energy? All right, how does that work? You know, we know that something can have energy. How does it work, and where do these formulas come from? Because they're kind of vague. Well, let's say that I have a ball. Okay, we'll draw a ball here. And we'll draw a free body diagram with all the forces acting on it. Okay, and if the ball is on solid ground, then we know that the ball is a force going down due to gravity. Alright, because of acceleration due to gravity, and it has a force going up, which is the normal force. And these two forces are equal and opposite, which means there is no net force. So what's the acceleration? 0. The velocity here is 0 because it's on the ground. Now what if the ball is moving up with a constant velocity? Alright, so it's moving up with a constant velocity. What will its displacement be? It'll change linearly. You know from kinematics, if we take this to be the ground, x equals 0, then we know that its displacement will change linearly with time. Okay, so it'll go up linearly. Alright? And we know that there isn't a net force on it. So what do we know then? Well, we know that it has a force going down. And so we know that there has to be an equal and opposite force going up in order to keep it moving with a constant velocity. Okay, and going down, the force is Fg. So going up, the magnitude of the force has to equal Fg. Alright, and so what's Fg? What's the magnitude of the gravitational force? Well, it's the mass of the ball times gravity, times 9.81. So this is the magnitude of the ball, of the force being applied to move the ball up. Okay, because it's going up with a constant velocity. So when it gets to any point, okay, what's its energy? It's mgh times the distance off the ground. Well, that's interesting. Okay, because that is, so we know that the energy, potential energy from gravity is equal to mgh, which also happens to equal this applied force. Okay, it happens to equal the applied force times height. The height is moved up because this here force is equal to Fg. Alright, so what can we say? Well, we can say that the potential energy is equal to force times displacement up it was moved. Okay, and this quantity, force times displacement, it has a special name. Alright, because that quantity is what we call work. Alright, so work is equal to force times displacement. And why I'm bringing this up? Because this right here is equal to the change in energy. Okay, work changes energy. So when I gave you that gravitational potential energy from gravity is equal to mass times gravity times the height off the ground. The reason for this is because this quantity is the work done by any force in order to lift an object up to a height h. Alright, that's the work done because work changes energy. This here is called the work energy theorem. Okay, and so we can use this work energy theorem, and what we can do is we can draw a graph. Alright, we can draw a graph. We have displacement here, and we have force here. Alright? And say we have a graph that looks something like this. Well, work is force times displacement. So what's the work here? Well, we can zoom in on this. Alright, we can look at a small amount. A small amount of work is equal to a value of force times a small amount of displacement. Alright? And this is just a rough approximation. And we can add all of these values together until we get the entire graph. And that would give us a close approximation to the total work. And what happens when we keep adding all these values together and we use smaller and smaller approximations for these changes? We'll get the area under the graph. Alright, and this is a tool from calculus that we can use to find an area under the graph. And what does it mean? It means that we're going to take all these values of force and multiply them by a small value of displacement, because that's equal to a small value of work. So each area of these rectangles is equal to a small value of work. And when we add all these together, we could find the total work done by this force that's changing as displacement changes. Okay, and we're going to put this in our magic calculus tools. When we put this in our magic calculus tools, we find that work is equal to 1/2 mvf squared, final velocity squared, minus 1/2 mass times initial velocity squared. That's interesting, because what did we say these were? These were the kinetic energies. So we know that the work done to lift an object up, okay, you have an object and you lift it up to get it to a certain point H, that work is equal to the change in gravitational potential energy, or MGH. And we know that if you do work on it, okay, if you do any work, not even in this context, alright, so if you were to even have just a box, and you were to apply a force on the box, the work done by this force will result in the change of kinetic energy, because work changes energy. Alright, so this quantity of force times displacement is equal to work is equal to the change in energy.